CIET NCERT presents the audiobook Ganit Prakash, Textbook of Mathematics for Grade 6.
Page number 151. Chapter number 7. Fractions. Recall that when some whole number of things are shared equally among some number of people, fractions tell us how much each share is. Shabnam says, do you remember? If one roti is equally divided between two children, how much roti will each child get? Mukta says, each child will get half a roti. Shabnam says, the fraction 1/2 is written as 1/2. We also sometimes read this as 1/2. There is a picture given of a roti and two children. The roti is divided into two parts here. Mukta says if one roti is equally shared among 4 children, how much roti will one child get? Shabnam answers, each child's share is 1/4 roti. Mukta says, and which is more, 1/2 roti or 1/4 roti? Shabnam, when two children share one roti equally, each child gets 1/2 roti. When 4 children share one roti equally, each child gets 1/4 roti. Since in the second group more children share the same roti, each child gets a smaller share, so 1/2 roti is more than 1/4 roti. So 1/2 is greater than 1/4. Here on the right side you find a picture of a roti divided into 4 parts and 4 children standing near the roti. Page number 152. 7.1 Fractional units and equal shares. Benny, which fraction is greater, 1/5 or 1/9? Arvin, 9 is bigger than 5. So, I would guess that 1/9 is greater than 1/5. Am I right? Benny answers, no. That is a common mistake. Think of these fractions as shares. Arvin answers, if one roti is shared among 5 children, each one gets a share of 1/5 roti. If one roti is shared among 9 children, each one gets a share of 1/9 roti. Benny, exactly. Now think again. Which share is higher? Arvin, if I share with more people, I will get less. So, 1/9 is less than 1/5. Benny, you got it. Oh, so 1/100 is bigger than 1/200? When one unit is divided into several equal parts, each part is called a fractional unit. These are all fractional units: 1/2, 1/3, 1/4, 1/5, 1/6, and so on, 1/10, 1/50, and 1/100, etc. We also sometimes refer to fractional units as unit fractions. Figure it out. Fill in the blanks with fractions. Question number 1. 3 guavas together weigh 1 kg. If they are roughly of the same size, each guava will roughly weigh dash kg. Question number 2. A wholesale merchant packed 1 kg of rice in 4 packets of equal weight. The weight of each packet is dash kg. Question number 3. 4 friends ordered 3 glasses of sugarcane juice and shared it equally among themselves. Each one drank dash glass of sugarcane juice. Page number 153. Question number 4. The big fish weighs 1 upon 2 kg. The small one weighs 1 upon 4 kg. Together they weigh dash kg. Knowledge from the past. Fractions have been used and named in India since ancient times. In the Rig Veda, the fraction 3 upon 4 is referred to as Tripada. This has the same meaning as the words for 3 upon 4 in many Indian languages today. Example, teen pav in colloquial Hindi and mukkal in Tamil. Indeed, words for fractions used today in many Indian languages go back to ancient times. Find out and discuss the words for fractions that are used in the different languages spoken in your home, city, or state. Ask your grandparents, parents, teachers, and classmates what words they use for different fractions, such as for 1.5, 3/4, 1.25, half, quarter, and 2.5, and write them here. 5. Arrange these fraction words in order of size from the smallest to the biggest in the empty box given here. 1.5, 3/4, 1.25, half, quarter, 2.5. Write your answers in the box provided here. Page number 154. 7.2 Fractional units as part of a whole. The picture given here represents a whole chicky, which is made up of groundnut and jaggery. A picture of the chicky broken into 2 pieces is given here. How much of the original chicky is each piece? The picture represents 3/4. We can find that the bigger piece has 3 pieces of 1/4 chicky in it. So, we can measure the bigger piece using the fractional unit 1/4. We find that the bigger piece is 3/4 chicky. There is one more picture given. A whole chicky cut into 6 equal pieces. So, one piece will be how much? 1/6. The whole chicky is cut into 6 equal pieces in a different way. You can find a picture of the same here, which represents 1/6. By dividing the whole chicky into 6 equal parts in different ways, we get 1/6 chicky pieces of different shapes. Are they of the same size? Page number 155. What is the fractional unit of chicky given here? We have a whole chicky and 1/3 of the chicky represented here. We get this piece by breaking the chicky into 3 equal pieces. So this is 1/3 chicky. Figure it out. The figures here represent different fractional units of a whole chicky. How much of a whole chicky is each piece? We have here 8 different pictures with blank spaces. You need to find out the correct answers and write down in the boxes provided. Page number 156. 7.3 Measuring using fractional units. Take a strip of paper. We consider this paper strip to be 1 unit long. Fold the strip into 2 equal parts and then open up the strip again. Taking the strip to be 1 unit in length, what are the lengths of the 2 new parts of the strip created by the crease? Obviously, 1 upon 2 and another one also 1 upon 2. What will you get if you fold the previously folded strip again into 2 equal parts? You will now get 4 equal parts. So each part will be 1 upon 4 and 2 parts will be 2 times 1 upon 4, that is equal to 2 upon 4, and 3 parts will be 3 times 1 upon 4, that is equal to 3 upon 4. And what about the whole parts? 4 times 1 upon 4 is equal to 4 upon 4. Do it once more and fill in the blank boxes provided. Page number 157. Here we have another picture of a strip which is divided into 8 parts. So, one part will be 1 upon 8 and 2 parts will be 2 times 1 upon 8, that is equal to 2 upon 8 or 1 upon 4. 4 times 1 upon 8 will be equal to 4 upon 8, that is 1 upon 2. 6 times 1 upon 8 will be equal to 6 upon 8, that is equal to 3 upon 4. 8 times 1 upon 8 will be equal to 8 upon 8, that is equal to 1. Fractional quantities can be measured using fractional units. Let us explore another example here. We have a round figure which represents a full roti as a whole. In the first column, we have half of a roti given here, that is 1 upon 2 is equal to 1 times half. In the second column, we have one roti divided into 2 parts, 1 by 2 plus 1 by 2, that is equal to 2 times half. In the third column, we have 3 half rotis, 1 by 2 plus 1 by 2 plus 1 by 2, that is equal to 3 times half. In the fourth column, we have 4 half rotis. So 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2, that is equal to 4 times half. In the fifth column, we have 5 half equal rotis, 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2, that is equal to 5 times half. We can describe how much the quantity is by collecting together the fractional units. Page number 158. Figure it out. Question number 1. Continue this table of 1 by 2 for 2 more steps. Second, can you create a similar table for 1 upon 4? Third, make 1 by 3 using a paper strip. Can you use this to also make 1 upon 6? Fourth, draw a picture and write an addition statement as above to represent A. 5 times 1 by 4 of a roti, B. 9 times 1 by 4 of a roti. 5. Match each fractional unit with the correct picture. We have 3 different pictures given here. One of them has 1 by 3 portion shaded. Another one has 1 by 5 and next 1 upon 8 and 1 upon 6. We find different portions shaded here. You need to match each fractional unit with the correct picture. Reading fractions. We usually read the fraction 3 by 4 as 3 quarters or 3 upon 4. But reading it as 3 times 1 upon 4 helps us to understand the size of the fraction because it clearly indicates what the fractional unit is, 1 upon 4, and how many such fractional units, 3, there are. Recall what we call the top number and the bottom number of fractions. In the fraction 5 upon 6, 5 is the numerator and 6 is the denominator. Teacher's note. Give several opportunities to the children to explore the idea of fractional units with different shapes like circles, squares, rectangles, triangles, etc. Page number 159. 7.4 Marking fractional length on the number line. We have marked lengths equal to 1, 2, 3, etc. units on the number line. Now let us try to mark lengths equal to fractions on the number line. What is the length of the blue line? Write the fraction that gives the length of the blue line in the box. Here we have a number line which is having representation with mark 0, dash, 1, dash, 2. And blue line is between 0 and a dash. The distance between 0 and 1 is 1 unit long. It is divided into 2 equal parts. So, the length of each part is 1 upon 2 unit. So, this blue line is 1 upon 2 unit long. Now, can you find the lengths of the various blue lines given here? Fill in the boxes as well. First, here the fractional unit is dividing a length of 1 unit into 3 equal parts. Write the fraction that gives the length of the blue line in the box or in your notebook. We have a number line here with markings 0, 1 upon 3, dash, 1, dash, 2. Second one, here a unit is divided into 5 equal parts. Write the fraction that gives the length of the blue lines in the respective boxes or in your notebook. We have a number line here with markings as 0, 1 upon 5, dash, 3 upon 5, dash, 1. And we have here 4 dashes with 2 as the last marking. There is a blue mark line between 0 and a dash and 0 and a dash before 1. 3. Now, a unit is divided into 8 equal parts. Write the appropriate fractions in your notebook. Page number 160. Figure it out. First, on a number line, draw lines of length 1 upon 10, 3 upon 10 and 4 upon 5. Second, write 5 more fractions of your choice and mark them on the number line. Third, how many fractions lie between 0 and 1? Think, discuss with your classmates and write your answer. Fourth, what is the length of the blue line and black line given here? The distance between 0 and 1 is 1 unit long and it is divided into 2 equal parts. The length of each part is 1 upon 2. So, the blue line is 1 upon 2 units long. Write the fraction that gives the length of the black line in the box. We have here number line with the markings 0, 1 upon 2, 1, blank and then 2. There's a blue marking between 0 and 1 by 2. And the black line is between 0 and a dash. Fifth one. Write the fraction that gives the lengths of the black line in the respective boxes. We have a number line representing 0, 1 by 5, 2 by 5, 3 by 5, 4 by 5, 1. Then we have a blank boxes equally spaced which are 4 in number. And then we have 2. So, the black line is between 0 and the first blank box. Another black line is between 0 and the second blank box. Third black line is between 0 and third blank box. And fourth line is between 0 and the fourth blank box. Teacher's note. Draw these lines on the board and ask the students to write the answers in their notebooks. Page number 161. 7.5 Mixed fractions. Fractions greater than 1. You marked some fractions on the number line earlier. Did you notice that the lengths of all the blue lines were less than 1 and the lengths of all the black lines were more than 1? Write down all the fractions you marked on the number line earlier. Now, let us classify these in 2 groups. We are given 2 columns here. One is for the lengths less than 1 unit. Other one is for lengths more than 1 unit. Did you notice something common between the fractions that are greater than 1? In all the fractions that are less than 1 unit, the numerator is smaller than the denominator, while in the fractions that are more than 1 unit, the numerator is larger than the denominator. We know that 3 by 2, 5 by 2 and 7 by 2 are all greater than 1 unit. But can we see how many whole units they contain? 3 by 2 is equal to 1 by 2 plus 1 by 2 plus 1 by 2. That is equal to 1 plus 1 by 2. 5 upon 2 is equal to 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2. That is equal to 2 plus 1 upon 2. Here, there is a picture of a girl who says, I know that 1 upon 3 plus 1 upon 3 plus 1 upon 3 is equal to 3 upon 3, that is equal to 1. If I add one more 1 upon 3, I will get more than 1 unit. So, 4 upon 3 is greater than 1. Page number 162. Figure it out. Question number 1. How many whole units are there in 7 upon 2? Question number 2. How many whole units are there in 4 upon 3 and in 7 upon 3? Writing fractions greater than 1 as mixed numbers. We saw that 3 upon 2 is equal to 1 plus 1 upon 2. We can write other fractions in a similar way. For example, 4 upon 3 is equal to 1 upon 3 plus 1 upon 3 plus 1 upon 3 plus 1 upon 3. That is equal to 1 plus 1 upon 3, as 3 into 1 upon 3 is equal to 1. Figure it out. Question number 1. Figure out the number of whole units in each of the following fractions. A. 8 upon 3. B. 11 upon 5. C. 9 upon 4. We found that 8 upon 3 can be written as 2 plus 2 upon 3, where 8 upon 3 is a fraction and 2 plus 2 upon 3 is a mixed number. This number is thus also called 2 and 2/3. We also write it as 2 whole 2 upon 3. Question number 2. Can all fractions greater than 1 be written as such mixed numbers? A mixed number or mixed fraction consists a whole number called the whole part and a fraction that is less than 1 called the fractional part. Question number 3. Write the following fractions as mixed fractions. Example, 9 upon 2 is equal to 4 whole 1 upon 2. A. 9 upon 2. B. 9 upon 5. C. 21 upon 19. D. 47 upon 9. E. 12 upon 11. F. 19 upon 6. Page number 163. Here we find pictures of two children. One asking, can we write a mixed number, that is mixed fraction, as a regular fraction? The other one wonders, yes, I figured out a way to write a mixed number as a regular fraction. Jaya says, when I have 3 plus 3 upon 4, this means 1 plus 1 plus 1 plus 3 upon 4. I know 1 is equal to 1 upon 4 plus 1 upon 4 plus 1 upon 4 plus 1 upon 4. So, I get 1 upon 4 plus 1 upon 4 plus 1 upon 4 plus 1 upon 4 4 times, that is equal to 15 upon 4. Therefore, 4 into 1 upon 4 plus 4 into 1 upon 4 plus 4 into 1 upon 4 plus 3 into 1 upon 4 is equal to 15 upon 4. Figure it out. Write the following mixed numbers as fractions. A. 3 whole 1 upon 4. B. 7 whole 2 upon 3. C. 9 whole 4 upon 9. D. 3 whole 1 upon 6. E. 2 whole 3 upon 11. F. 3 whole 9 upon 10. 7.6 Equivalent fractions. Using a fraction wall, we find equal fractional lengths. In the previous section, you used paper folding to represent various fractions using fractional units. Let us do some more activities with the same paper strips. Page number 164. We have a paper strip of 1 unit length. On folding it into two halves, we have 1/2 as each part. Now again, fold it to have 4 equal parts. So, half will be equal to 2/4. Now fold it again to get 8 equal parts. So, half of the strip will be equal to 4/8. What do you explore here? Are the lengths 1/2 and 2/4 equal? Are the lengths 2/4 and 4/8 equal? We can say that 1/2 is equal to 2/4 is equal to 4/8. These are equivalent fractions that denote the same length, but they are expressed in terms of different fractional units. Now check whether 1/3 and 2/6 are equivalent fractions or not using the paper strips. Make your own fraction wall using such strips as given in the figure here. Answer the following questions after observing the fraction wall. First one, are the lengths 1/2 and 3/6 equal? Second, are 2/3 and 4/6 equivalent fractions? Why? Third, how many pieces of lengths 1/6 will make a length of 1/2? Fourth, how many pieces of length 1/6 will make a length of 1/3? We can find a picture of the same represented here. Page number 165. We can extend this idea to make a fraction wall up to the fractional unit 1/10. This fraction wall is given at the end of the book. Figure it out. First, are 3/6, 4/8, 5/10 equivalent fractions? Why? Question number 2. Write two equivalent fractions for 2/6. Question number 3. 4/6 is equal to dash is equal to dash is equal to dash is equal to. Write as many as you can. Understanding equivalent fractions using equal shares. One roti was shared equally by 4 children. What fraction of the whole did each child get? The figure given here represents the division of a roti among 4 children. Fraction of a roti each child got is 1/4. The 4 shares must be equal to each other. We find a picture of a roti divided into 4 parts. So, each part is represented as 1/4. Page number 166. You can also express this event through division facts, addition facts, and multiplication facts. The division fact is 1 divided by 4 is equal to 1/4. The addition fact is 1 is equal to 1/4 plus 1/4 plus 1/4 plus 1/4. The multiplication fact is 1 is equal to 4 into 1/4. Figure it out. First, 3 rotis are shared equally by 4 children. Show the division in the picture and write a fraction for how much each child gets. Also write the corresponding division facts, addition facts and multiplication facts. Fraction of roti each child gets is dash. Division fact is equal to dash. Addition fact is equal to dash. Multiplication fact is equal to dash. Compare your picture and answers with your classmates. We have a picture of 3 rotis each divided into 4 equal parts. Question number 2. Draw a picture to show how much each child gets when 2 rotis are shared equally by 4 children. Also, write the corresponding division facts, addition facts and multiplication facts. Question number 3. Anil was in a group where 2 cakes were divided equally among 5 children. How much cake will Anil get? Here we find picture of a girl asking, now if there are 10 children in my group, how many cakes will I need so that they get same amount of cake as Anil? She wonders, what if we put 2 such groups together? One group where 2 cakes are divided equally between 5 children and another group again with 4 cakes and 10 children. Page number 167. We have a picture here of group 1 representing 2 rectangles and 5 children. In group 2, we have 4 boxes which are rectangular in shape and 5 children in each group. So, the share of each child is the same in both these situations. So, 2 upon 5 is equal to 4 upon 10. Let us examine the shares of each child in the following situations. 1 roti is divided equally between 2 children. 2 rotis are divided equally among 4 children. 3 rotis are divided equally among 6 children. Let us draw and share. Did you notice that in each situation the share of every child is the same? So, we can say that 1 upon 2 is equal to 2 upon 4, that is equal to 3 upon 6. We find pictures given here. In the first one, we can find out 1 roti is divided equally between 2. So, each part is 1 upon 2. In the second picture, we find 2 rotis are divided equally among 4. So, we can find 2 rotis divided into 4 parts. So, each part is 2 upon 4. In the third picture, we find 3 rotis are divided equally among 6. So, each part will be equal to 3 upon 6. Fractions where the shares are equal are called equivalent fractions. Page number 168. So, 1 upon 2, 2 upon 4 and 3 upon 6 are all equivalent fractions. Find some more fractions equivalent to 1 upon 2. Write them in the boxes here. We have 4 boxes provided to you. Equally divide the rotis in the situations and write down the share of each child. Are the shares in each of these cases the same? Why? In the first picture, 2 rotis divided equally among 3 children. So each part is 2 upon 3. In the next picture, 4 rotis divided equally among 6 children. You need to write down the part in each case. In the third picture, 6 rotis divided equally among 9 children. You need to write down in the blank boxes provided. 2 by 3 is also called the simplest form of 4 upon 6. It is also the simplest form of 6 by 9 as well. The picture shows the girl is asking, do you notice anything about the relationship between the numerator and denominator in each of these fractions? Figure it out. Find the missing numbers. A. 5 glasses of juice shared equally among 4 friends is the same as dash glasses of juice shared equally among 8 friends. So, 5 upon 4 is equal to dash upon 8. B. 4 kg of potatoes divided equally in 3 bags is the same as 12 kgs of potatoes divided equally in dash bags. So, 4 upon 3 is equal to 12 upon dash. Page number 169. C. 7 rotis divided among 5 children is the same as dash rotis divided among dash children. So, 7 upon 5 is equal to dash upon dash. In which group will each child get more chicky? 1 chicky divided between 2 children or 5 chickies divided among 8 children? Mukta. So, we must compare 1 upon 2 and 5 upon 8. Which is more? Shabnam says, well, we have seen that 1 upon 2 is equal to 4 upon 8. And clearly, 4 upon 8 is less than 5 upon 8. So, the children for whom 5 chickies is divided equally among 8 will get more than those children for whom 1 chickie is divided equally among 2. The children of the second group will get more chickie each. What about the following groups? In which group will each child get more? 1 chickie divided between 2 children or 4 chickies divided among 7 children? Shabnam. The children of which group will get more chickie this time? Mukta says we must compare 1 upon 7 and 4 upon 7. Now, 1 into 4 upon 2 into 4 is equal to 4 upon 8. So, 1 upon 2 is equal to 4 upon 8. Shabnam says, but why did you multiply the numerator and denominator by 4 again? Mukta says, you will observe, when 4 chickies are divided equally among 7 children, each one will get 4 upon 7 chickie. When 4 chickies are divided equally among 8 children, each one will get 4 upon 8 chickie. So, 4 upon 7 is greater than 4 upon 8. Page number 170. The little girls wonder if the number of units that are shared is the same, but the number of children among whom the units are shared is more, then the share is less. The other girl says, therefore, 4 by 7 is greater than 4 upon 8 and 4 by 8 is equal to 1 upon 2. So, 4 by 7 is greater than 1 upon 2. Now I understood why you multiplied the numerator and denominator by 4. Suppose the number of children is kept the same, but the number of units that are being shared is increased. What can you say about each child's share now? Why? Discuss how your reasoning explain. 1 upon 5 is less than 2 by 5. 3 upon 7 is less than 4 by 7. And 1 by 2 is less than 5 upon 8. Now decide in which of the two groups will each child get a larger share. First one, group 1. 3 glasses of sugarcane juice divided equally among 4 children. Group 2. 7 glasses of sugarcane juice divided equally among 10 children. Second one, group 1. 4 glasses of sugarcane juice divided equally among 7 children. Group 2. 5 glasses of sugarcane juice divided equally among 7 children. Which groups were easier to compare? Why? Shabnam says to compare the first two groups, we have to find fractions equivalent to the fractions 3 upon 4 and 7 upon 10. Mukta says, how about 6 upon 8 is equal to 3 upon 4 and 21 upon 30 is equal to 7 upon 10? The girl wonders, when the number of children is same, it is easier to compare, isn't it? Page number 171. Shabnam, there is a condition. The fractional unit used for the two fractions have to be the same, like 2 by 6 and 3 by 6. Both use the same fractional unit 1 upon 6. That is, the denominators are the same. But 6 upon 8 and 21 upon 30 do not use the same fractional units. They have different denominators. Mukta says, okay. So let us start making equivalent fractions then. 3 upon 4 is equal to 6 upon 8 is equal to 9 upon 12 is equal to 12 upon 16, that is equal to 15 upon 20. But when do I stop? Shabnam says, got it. How about we go on till 4 into 10 is equal to 40? Mukta says, you mean the product of the two denominators? Sounds good. We have 3 upon 4 and 7 upon 10. The product of the two denominators, 4 and 10, is 40. So 3 upon 4 is equal to 6 upon 8, that is equal to 9 upon 12, equal to 12 upon 16, equal to 15 upon 20, is equal to 18 upon 24, is equal to 27 upon 36, is equal to 30 upon 40. Go till we reach the denominator 40. Likewise, 7 upon 10 is equal to 14 upon 20, is equal to 21 upon 30, is equal to 28 upon 40. The two little girls wonder, but notice that 15 upon 20 and 14 upon 20 also had the same denominator. The other girl says, yes, we just needed to get the same fractional units for each fraction. Shabnam says, so fractions equivalent to 3 by 4 and 7 upon 10 with the same fractional unit, that is same denominators, are 30 upon 40 and 28 upon 40, or 15 upon 20 and 14 upon 20. Since clearly 30 upon 40 is greater than 28 upon 40, we conclude that 3 upon 4 is greater than 7 upon 10. Page number 172. Find equivalent fractions for the given pairs of fractions such that the fractional units are the same. A. 7 upon 2 and 3 upon 5. B. 8 upon 3 and 5 upon 6. C. 3 upon 4 and 3 upon 5. D. 6 upon 7 and 8 upon 5. E. 9 upon 4 and 5 upon 2. F. 1 upon 10 and 2 upon 9. G. 8 upon 3 and 11 upon 4. H. 13 upon 6 and 1 upon 9. Expressing a fraction in lowest terms or in its simplest form. In any fraction, if its numerator and denominator have no common factor except 1, then the fraction is said to be in lowest terms or in its simplest form. In other words, a fraction is said to be in lowest terms if its numerator and denominator are as small as possible. Any fraction can be expressed in lowest terms by finding an equivalent fraction whose numerator and denominator are as small as possible. Let's observe how to express fractions in lowest terms. Example, is the fraction 16 upon 20 in lowest terms? No, 4 is a common factor of 16 and 20. Let us reduce 16 upon 20 to lowest terms. We know that both 16 numerator and 20 denominator are divisible by 4. So, 16 divided by 4 upon 20 divided by 4 is equal to 4 upon 5. Now, there is no common factor between 4 and 5. Hence, 16 upon 20 expressed in lowest terms is 4 upon 5. So, 4 upon 5 is called the simplest form of 16 upon 20 since 4 and 5 have no common factor other than 1. The girl wonders any fraction can be converted to lowest terms by dividing both the numerator and denominator by the highest common factor between them. Page number 173. Expressing a fraction in lowest terms can also be done in steps. Suppose we want to express 36 upon 60 in lowest terms. First, we notice that both the numerator and denominator are even. So, we divide both by 2 and see that 36 upon 60 is equal to 18 upon 30. Both the numerator and denominator are even again. So, we can divide them each by 2 again. We get 18 upon 30 is equal to 9 upon 15. We now notice that 9 and 15 are both multiples of 3. So, we divide both by 3 to get 9 upon 15 is equal to 3 upon 5. Now, 3 and 5 have no common factor other than 1. So, 36 upon 60 in lowest terms is 3 upon 5. Alternatively, we could have noticed that in 36 upon 60, both the numerator and denominator are multiples of 12. We can observe that 36 is equal to 3 into 12 and 60 is equal to 5 into 12. Therefore, we could have concluded that 36 upon 60 is equal to 3 upon 5 straight away. Either method works and will give the same answer, but sometimes it can be easier to go in steps. Figure it out. Express the following fractions in lowest terms. A. 17 upon 51. B. 64 upon 144. C. 126 upon 147. D. 525 upon 112. 7.7. Comparing fractions. Which is greater, 4 by 5 or 7 upon 9? It can be difficult to compare two such fractions directly. However, we know how to find fractions equivalent to two fractions with the same denominator. Let us see how we can use it. 4 upon 5 is equal to 4 into 9 upon 5 into 9. That is equal to 36 upon 45. 7 upon 9 is equal to 7 into 5 upon 8 into 5. That is equal to 35 upon 45. The girl observes that 45 is a common multiple of 5 and 9. So, we can use 45 as a common denominator. Page number 174. Clearly, 36 upon 45 is greater than 35 upon 45. So, 4 upon 5 is greater than 7 upon 9. Let us try this for another pair, 7 upon 9 and 17 upon 21. 63 is a common multiple of 9 and 21. We can then write 7 upon 9 is equal to 7 into 7 upon 9 into 7. That is equal to 49 upon 63. 17 upon 21 is equal to 17 into 3 upon 21 into 3. That is equal to 51 upon 63. Clearly, 49 upon 63 is less than 51 upon 63. So, 7 upon 9 is less than 17 upon 21. Let's summarize. Steps to compare the sizes of two or more given fractions. Step 1. Change the given fractions to equivalent fractions so that they all are expressed with the same denominator or same fractional unit. Step 2. Now compare the equivalent fractions by simply comparing the numerators, that is, the number of fractional units each has. Figure it out. Question number 1. Compare the following fractions and justify your answers. A. 8 upon 3, 5 upon 2. B. 4 upon 9, 3 upon 7. C. 7 upon 10, 9 upon 14. D. 12 upon 5 and 8 upon 5. E. 9 upon 4, 5 upon 2. Question number 2. Write the following fractions in ascending order. A. 7 upon 10, 11 upon 15 and 2 upon 5. B. 19 upon 24, 5 upon 6 and 7 upon 12. Question number 3. Write the following fraction in descending order. A. 25 upon 16, 7 upon 8, 13 upon 4 and 17 upon 32. B. 3 upon 4, 12 upon 5, 7 upon 12 and 5 upon 4. Page number 175. 7.8 Addition and subtraction of fractions. Meena's father made some chicky. Meena ate 1 upon 2 of it and her younger brother ate 1 upon 4 of it. How much of the total chicky did Meena and her brother eat together? We can find a picture of Chicky given here. We can arrive at the answer by visualizing it. Let us take a piece of Chicky and divide it into two halves like the one given in the picture. Meena ate 1/2 of it as given in the picture. Let us now divide the remaining half into two further halves as given in the picture. Each of these pieces is 1/4 of the whole Chicky. Meena's brother ate 1/4 of the whole Chicky as is observed in the picture. The total Chicky eaten is 1/2 by Meena and 1/4 by her brother. The total Chicky eaten is equal to 1/2 plus 1/4. That is equal to 1/4 plus 1/4 plus 1/4. That is equal to 3 into 1/4. That is equal to 3/4. How much of the total Chicky is remaining? We can find here the picture representing the fractional part the brother ate and Meena has eaten. So total Chicky eaten is 3 parts out of the 4 parts. Page number 176. Adding fractions with the same fractional unit or denominator. Example, find the sum of 2/5 and 1/5. Let us represent both using the rectangular strips. In both fractions, the fractional unit is the same, 1/5. So, each strip will be divided into 5 equal parts. So, 2/5 will be represented as, in the strip we can see in the picture, one strip has 5 parts, out of which 2 are colored red. And 1/5 will be represented as, we have another picture in which out of 5 parts, only one part is colored red. Adding the two given fractions is the same as finding out the total number of shaded parts, each of which represent the same fractional unit 1/5. In this case, the total number of shaded parts is 3. Since each shaded part represents the fractional unit 1/5, we see that the 3 shaded parts together represent the fraction 3/5. Therefore, 2/5 plus 1/5 is equal to 3/5. We have another picture here in which out of 5 parts, 3 parts are colored red. Remember, all the 5 parts are equal. Example, find the sum of 4/7 and 6/7. Let us represent both again using the rectangular strip model. Here, in both fractions, the fractional unit is the same, that is 1/7. So, each strip will be divided into 7 equal parts. Page number 177. Then 4/7 will be represented as one strip which is divided into 7 parts, out of which 4 are colored. And 6/7 will be represented as a strip divided into 7 parts, out of which 6 are colored. In this case, the total number of shaded parts is 10, and each shaded part represents the fractional unit 1/7. So, the 10 shaded parts together represent the fraction 10/7 as given here. Remember, while adding fractions with the same fractional unit, just add the number of fractional units from each fraction. Here we find one more picture given in which we have two strips with 7 parts each, and you have 4 parts colored in the first row and 6 parts colored in the second row. Therefore, 4 upon 7 plus 6 upon 7 is equal to 10 upon 7. That can be written as 1 plus 3 upon 7 or 1 whole 3 upon 7. This can also be observed in the picture that out of the two strips, the first strip of 7 parts is fully colored and the second strip of 7 parts has 3 parts colored. So total parts are how many? 10 parts which are colored out of 14 parts. Try adding 4 by 7 plus 6 by 7 using a number line. Do you get the same answer? Adding fractions with different fractional units or denominators. Example, find the sum of 1 by 4 and 1 by 3. To add fractions with different fractional units, first convert the fractions into equivalent fractions with the same denominator or fractional unit. Page number 178. In this case, the common denominator can be made 3 into 4 is equal to 12. That is, we can find equivalent fractions with fractional unit 1 upon 12. Let us write the equivalent fraction for each given fraction. 1 upon 4 is equal to 1 into 3 upon 4 into 3. That is equal to 3 upon 12. 1 upon 3 is equal to 1 into 4 upon 3 into 4. That is equal to 4 upon 12. Now, 3 upon 12 and 4 upon 12 have the same fractional unit, that is 1 upon 12. Therefore, 1 upon 4 plus 1 upon 3 is equal to 3 upon 12 plus 4 upon 12, that is equal to 7 upon 12. This method of addition, which works for adding any number of fractions, was first explicitly described in general by Brahmagupta in the year 628 CE. We will describe the history of the development of fractions in more detail later in the chapter. For now, we simply summarize the steps in Brahmagupta's method for addition of fractions. Brahmagupta's method for adding fractions. First, find equivalent fractions so that the fractional unit is common for all fractions. This can be done by finding a common multiple of the denominators. Example, the product of the denominators or the smallest common multiple of the denominators. 2. Add these equivalent fractions with the same fractional units. This can be done by adding the numerators and keeping the same denominator. 3. Express the result in lowest terms if needed. Let us carry out another example of Brahmagupta's method. Example, find the sum of 2 by 3 and 1 by 5. The denominators of the given fractions are 3 and 5. The lowest common multiple of 3 and 5 is 15. Then we observe that 2 upon 3 is equal to 2 into 5 upon 3 into 5. That is equal to 10 upon 15. 1 upon 5 is equal to 1 into 3 upon 5 into 3. That is equal to 3 upon 15. Page number 179. Therefore, 2 upon 3 plus 1 upon 5 is equal to 10 upon 15 plus 3 upon 15, that is equal to 13 upon 15. Example, find the sum of 1 by 6 and 1 by 3. The smallest common multiple of 6 and 3 is 6. 1 upon 6 will remain 1 upon 6. 1 upon 3 is equal to 1 into 2 upon 3 into 2. That is equal to 2 upon 6. Therefore, 1 upon 6 plus 1 upon 3 is equal to 1 upon 6 plus 2 upon 6, that is equal to 3 upon 6. The fraction 3 upon 6 can now be re-expressed in lowest terms if desired. This can be done by dividing both the numerator and denominator by 3, the biggest common factor of 3 and 6. So, 3 upon 6 is equal to 3 divided by 3 upon 6 divided by 3, that is equal to 1 upon 2. Therefore, 1 upon 6 plus 1 upon 3 is equal to 1 upon 2. Figure it out. Question number 1. Add the following fractions using Brahmagupta's method. A. 2 upon 7 plus 5 upon 7 plus 6 upon 7. B. 3 upon 4 plus 1 upon 3. C. 2 upon 3 plus 5 upon 6. D. 2 upon 3 plus 2 upon 7. E. 3 upon 4 plus 1 upon 3 plus 1 upon 5. F. 2 upon 3 plus 4 upon 5. G. 4 upon 5 plus 2 upon 3. H. 3 upon 5 plus 5 upon 8. I. 9 upon 2 plus 5 upon 4. J. 8 upon 3 plus 2 upon 7. K. 3 upon 4 plus 1 upon 3 plus 1 upon 5. L. 2 upon 3 plus 4 upon 5 plus 3 upon 7. M. 9 upon 2 plus 5 upon 4 plus 7 upon 6. Question number 2. Rahim mixes 2 by 3 liters of yellow paint with 3 upon 4 liters of blue paint to make green paint. What is the volume of green paint he has made? Question number 3. Geeta bought 2/5 meter of lace and Shamim bought 3 upon 4 meter of the same lace to put a complete border on a tablecloth whose perimeter is 1 meter long. Find the total length of the lace they both have bought. Will the lace be sufficient to cover the whole border? Page number 180. Subtraction of fractions with the same fractional unit or denominator. Brahmagupta's method also applies when subtracting fractions. Let us start with the problem of subtracting 4 upon 7 from 6 upon 7. That is, what is 6 upon 7 minus 4 upon 7? To solve this problem, we can again use the rectangular strips. In both fractions, the fractional unit is the same, that is 1 upon 7. Let us first represent the bigger fraction using a rectangular strip model as given here. We have a strip which is divided into 7 equal parts and 6 equal parts are colored with red color. Each shaded part represents 1 upon 7. Now, we need to subtract 4 upon 7. To do this, let us remove 4 of the shaded parts. We have a picture in which we can find the 4 parts are removed and the fractional parts to be removed are 4 here. We can do this here directly because both fractions have the same fractional units. So, we are left with two shaded parts, that is 6 upon 7 minus 4 upon 7 is equal to 2 upon 7. Try doing this same exercise using the number line. Page number 181. Figure it out. Question number 1. 5 upon 8 minus 3 upon 8. Question number 2. 7 upon 9 minus 5 upon 9. Question number 3. 10 upon 27 minus 1 upon 27. Subtraction of fractions with different fractional units or denominators. Example, what is 3 upon 4 minus 2 upon 3? As we already know, the procedure for subtraction of fractions with the same fractional units, let us convert each of the given fractions into equivalent fractions with the same fractional units. 3 upon 4 is equal to 3 into 3 upon 4 into 3, that is equal to 9 upon 12. Yes, by doing this, we can easily subtract the two fractions. Think, why did we choose to multiply both the numerator and denominator by 3? And similarly, 2 upon 3 is equal to 2 into 4 upon 3 into 4, that is equal to 8 upon 12. Again, why did we choose to multiply both the numerator and denominator here by 4? Therefore, 3 upon 4 minus 2 upon 3 is equal to 9 upon 12 minus 8 upon 12, that is equal to 1 upon 12. Brahmagupta's method for subtracting two fractions. First, convert the given fractions into equivalent fractions with the same fractional unit, that is, the same denominator. Second, carry out the subtraction of fractions having the same fractional units. This can be done by subtracting the numerators and keeping the same denominator. 3. Simplify the result into lowest terms if needed. Page number 182. Figure it out. Question number 1. Carry out the following subtractions using Brahmagupta's method. A. 8 upon 15 minus 3 upon 15. B. 2 upon 5 minus 4 upon 15. C. 5 upon 6 minus 4 upon 9. D. 2 upon 3 minus 1 upon 2. Question number 2. Subtract as indicated. A. 13 upon 4 from 10 upon 3. B. 18 upon 5 from 23 upon 3. C. 29 upon 7 from 45 upon 7. Question number 3. Solve the following problems. A. Jaya's school is 7 upon 10 kilometers from her home. She takes an auto for 1/2 kilometers from her home daily and then walks the remaining distance to reach her school. How much does she walk daily to reach the school? Part B. Jivika takes 10 upon 3 minutes to take a complete round of the park, and her friend Namit takes 13 upon 4 minutes to do the same. Who takes less time and by how much? 7.9. A pinch of history. Do you know what a fraction was called in ancient India? It was called bhin in Sanskrit, which means broken. It was also called bhag or ansh, meaning part or piece. The way we write fractions today globally originated in India. In ancient Indian mathematical texts such as the Bakshali manuscript from around the year 300 CE, when they wanted to write 1 upon 2, they wrote it as 1 upon 2, which is indeed very similar to the way we write it today. This method of writing and working with fractions continued to be used in India for the next several centuries, including by Aryabhatta in 499 CE, Brahmagupta in 628 CE, Sridharacharya c. 750 CE, and Mahavircharya c. 850 CE, among others. The line segment between the numerator and denominator in 1 upon 2 and the other fractions was later introduced by the Moroccan mathematician Al-Hazar in the 12th century. Over the next few centuries, the notation then spread to Europe and around the world. Page number 183. Fractions had also been used in other cultures such as the ancient Egyptian and Babylonian civilizations, but they primarily used only fractional units, that is, fractions with a 1 in the numerator. More general fractions were expressed as sums of fractional units, now called Egyptian fractions. Writing numbers as the sum of fractional units, example 19 upon 24 is equal to 1 upon 2 plus 1 upon 6 plus 1 upon 8, can be quite an art and leads to beautiful puzzles. We will consider one such puzzle given here. General fractions, where the numerator is not necessarily 1, were first introduced in India, along with their rules of arithmetic operations like addition, subtraction, multiplication, and even division of fractions. The ancient Indian treatise called the Sulba Sutras shows that even during Vedic times, Indians had discovered the rules for operations with fractions. General rules and the procedures for working with and computing with fractions were first codified formally and in a modern form by Brahmagupta. Brahmagupta's method for working with and computing with fractions are still what we use today. For example, Brahmagupta described how to add and subtract fractions as given here. By the multiplication of the numerator and the denominator of each of the fractions by the other denominators, the fractions are reduced to a common denominator. Then, in case of addition, the numerators obtained after the above reduction are added. In case of subtraction, their difference is taken. Brahmagupta, Brahmasabda Siddhanta, verse 12.2, 628 CE. The Indian concepts and methods involving fractions were transmitted to Europe via the Arabs over the next few centuries, and they came into general use in Europe in around the 17th century and then spread worldwide. Page number 184. Puzzle. It is easy to add up fractional units to obtain the sum 1 if one uses the same fractional unit. For example, 1 upon 2 plus 1 upon 2 is equal to 1. 1 upon 3 plus 1 upon 3 plus 1 upon 3 is equal to 1. 1 upon 4 plus 1 upon 4 plus 1 upon 4 plus 1 upon 4 is equal to 1, etc. However, can we think of a way to add fractional units that are all different to get 1? It is not possible to add two different fractional units to get 1. The reason is that 1 by 2 is the largest fractional unit and 1 by 2 plus 1 by 2 is equal to 1. To get different fractional units, we would have to replace at least one of the 1 by 2's with some smaller fraction unit, but then the sum would be less than 1. Therefore, it is not possible for two different fractional units to add up to 1. We can try to observe instead for a way to write 1 as the sum of three different fractional units. First, can you find three different fractional units that add up to 1? It turns out there is only one solution to this problem up to changing the order of the three fractions. Can you find it? Try to find it before reading further. Here is a systematic way to find the solution. We know that 1 upon 3 plus 1 upon 3 plus 1 upon 3 is equal to 1. To get the fractional units to be different, we will have to increase at least one of the 1 by 3's and decrease at least one of the other 1 by 3's to compensate for that increase. The only way to increase 1 by 3 to another fractional unit is to replace it by 1 upon 2. So, 1 by 2 must be one of the fractional units. Now, 1 by 2 plus 1 by 4 plus 1 by 4 is equal to 1. To get the fractional units to be different, we will have to increase one of the 1 by 4's and decrease the other 1 by 4 to compensate for that increase. Now, the only way to increase 1 by 4 to another fractional unit that is different from 1 upon 2 is to replace it by 1 by 3. Page number 185. So, two of the fractions must be 1 upon 2 and 1 upon 3. What must be the third fraction then, so that the three fractions add up to 1? This explains why there is only one solution to the above problem. Here we have a picture of a circle which is divided into 6 equal parts. In this picture, 3 parts are colored green, 1 part is colored blue, and 2 parts are colored brown. 1 upon 2 plus 1 upon 3 plus 1 upon 6 is equal to 1. What if we look for 4 different fractional units that add up to 1? Second question, can you find 4 different fractional units that add up to 1? It turns out that this problem has 6 solutions. Can you find at least one of them? Can you find them all? You can try using similar reasoning as in the cases of 2 and 3 fractional units, or find your own method. Once you find one solution, try to divide a circle into parts like in the given figure to visualize it. Page number 186. Summary. Fraction as equal share. When a whole number of units is divided into equal parts and shared equally, a fraction results. Fractional units. When one whole basic unit is divided into equal parts, then each part is called a fractional unit. Reading fractions. In a fraction, such as 5 upon 6, 5 is called the numerator and 6 is called the denominator. Mixed fractions contain a whole number part and a fractional part. Number line. Fractions can be represented on a number line. Every fraction has a point associated with it on the number line. Equivalent fractions. When two or more fractions represent the same share or number, they are called equivalent fractions. Lowest terms. A fraction whose numerator and denominator have no common factor other than 1 is said to be in lowest terms or in its simplest form. Brahmagupta's method for adding fractions. When adding fractions, convert them into equivalent fractions with the same fractional unit, that is, the same denominator, and then add the number of fractional units in each fraction to obtain the sum. This is accompanied by adding the numerators while keeping the same denominator. Brahmagupta's method for subtracting fractions. When subtracting fractions, convert them into equivalent fractions with the same fractional unit, that is, the same denominator, and then subtract the number of fractional units. This is accomplished by subtracting the numerators while keeping the same denominator. This is the end of the chapter 7.
Ganit Prakash, you were just listening to this audio book, Textbook of Mathematics for Grade 6. Narration, Swarnlata. Academic Coordinator, Dr. Prakash Vadigar. Technical Coordination, Bati Langlingdo. Sound Recordist, Manju Kumari. Assistance in Production, Soumya Malik. Directed and produced by Vimlesh Chaudhary. This audiobook is presented to you by CIET NCERT, New Delhi, India.